The chemical industry is an integral part of the modern economy, producing medicines, cosmetics, raw materials, cooking ingredients, fuel for your car, and on and on. The silent workhorse powering this plethora of products is the catalyst, a special type of chemical that speeds up a reaction, allowing more to be made in less time. Now an integral part of the chemical industry, a lot of work has gone into developing better catalysts. But as demand for chemicals continues to grow, the catalysts themselves have started to shrink. Let's take a closer look and learn why. As a particle becomes smaller, a higher amount of material is present on the surface. Only the atoms on the surface participate in a reaction, so having more atoms on the surface means less wasted space. That means catalysts made of precious metals don't need as much material, and why catalytic converters are affordable for use in cars even though they use platinum. These catalyst particles might be so small that they're only nanometers long. These kinds of particles are called nanoparticles. Oftentimes, catalyst designers will use more than one metal to take advantage of the strengths and weaknesses of each component. But with more components comes greater complexity, and the atoms can arrange themselves in many different ways in the particle. Some arrangements are more favorable than others, and this favorability is measured by cohesive energy. Cohesive energy is the energy holding all the atoms together in the particle. Until recently, this was difficult to calculate, requiring a supercomputer for most particles. But now with the bond-centric model, it can be calculated easily. The bond-centric model is an improvement on the older short-range bond-cutting model from the 1980s, which only worked on particles with one type of element. Our improvements allow the bond-centric model to account for bimetallic systems with ease. The model is called bond-centric because it focuses only on the bonds between atoms. Let's take a look at an example at these two atoms in the system. The model looks at atoms A and B and first takes into account the cohesive energy of the bulk unit cell, the number of bonds called the coordination number in the bulk unit cell, their current coordination number, and a special constant called a gamma value. The gamma value is the special sauce that lets the bond-centric model account for bimetallics with accuracy. Both A and B have their own gamma value, and they must add up to 2. In addition, they satisfy the following equation. The bond association energy of the A2 dimer times the gamma A coefficient, plus the bond association energy of the B2 dimer times the gamma B coefficient, is equal to 2 times the AB bond association energy. With this value, we have everything we need to calculate a cohesive energy using the bond-centric model. For now, let's consider just one shape, size, and composition for an arbitrary system of two metals. Recall that there are a lot of different ways the atoms can arrange themselves, and we need the bond-centric model to have any hope of looking at a decent fraction of them. One thing we might try is just randomly generating a bunch of different chemical orderings, that is, the way the atoms arrange themselves in the particle. But there's a faster way we can optimize the chemical ordering. We can use a genetic algorithm. With a genetic algorithm, we start with a population of different chemical orderings. We then rank them by their cohesive energy. The winner is the particle with the strongest cohesive energy. The worst are thrown away. We then keep the best particles, make new particles using different parts of the best particles, and fill the rest in with new random particles. This whole process of creating new particles, ranking them, and starting over is called a generation. After many generations, we get better and better particles, and get closer and closer to the best we can possibly make. The best particles we can make are, hopefully, what might be synthesized in a real solution. This allows us to make better guesses as to what the structure really looks like, which gives us a better understanding of what's really happening in the flask, which lets us make better catalysts, which lets the chemical industry do more with less in less time.